How are you guys?
Good, how are you?
Yes, sir.
Thank you. Solomon. Solomon Harris, Gage Levine.
Morning.
Yes. Briggs, Paul Mustaine, Will Hostetler, Nathan Light, Nick Markey, Quinn Hart, Ismail Taylor. Good. Yeah, that's good. Okay, guys, so let's start the last chapter. Last chapter is nothing but the inverse Laplace transform and the Laplace transform and its inverse Laplace transform. So that is a last chapter. Right, guys? Okay. Again, this is another formula set which you need to take the print out for your final in the last exam. Inverse Laplace transform and Laplace transform. I'm not going to take this one right now, but I need this one after some time, after 15-20 minutes. So let me start with this one. First of all, let me let you know what we mean by the Laplace transform. Guys, please keep in mind this thing that Laplace transform is one kind of transformation which converts one function to another function. Just like differentiation. Differentiation is a transformation which converts one function to another function in terms of its derivative. Like x derivative, if you apply this differential transform to sine x, you are going to get cosine x. If you apply to cosine x, you're going to get negative of sine x, like this. If you apply to x square, you're going to get 2x, like this. So that is the differential transform. Same with the integral transform. So if you apply one parabola and integral transform on a parabola, you're going to get x cubed by 3, like this. So differentiation, integration, these are just the transforms which converts one function to another function. Parabola is converted to linear line over here. Parabola is converted to cubic equation, cubic curvature here. So this way we have another transformation that is called the integral transformation. The general form of the integral transformation is integration 0 to infinity kts ff dt. Kts ft dt, where k is a kernel of the transformation. And because it is an indefinite integral, improper integral, I would say, of first kind. So let me just fix one point over here instead of infinity, and then after we will allow this b tends to infinity. The limit b tends to infinity, 0 to b k st f of t dt. And we can calculate this, we can find this limit. Okay, definition of Laplace transform is Laplace, he figured it out, this transform, that's why it is called the Laplace transform. Here you can see Laplace transform starts with 0, goes up to infinity. That means all transformations, all Laplace transformations, they are based on the improper integral of first kind, your Calc 2 course. Okay. If you take negative infinity to infinity, e to the power negative st and f dt, something like that, then it is ist actually. So this Laplace transform is converted to Fourier transform. So the other way around, I would say that Fourier transform, that is the generalized version of the Laplace transform. Fourier transform is more generalized to Laplace transform. Okay, so Laplace, right now we are just focusing over here on Laplace transform. As I told you, there are plenty of integral transform. So Fourier, Laplace transform, Fourier transform, Henkel transform, Bessel transforms, lots of transformations are there. Out of these integral transformations, we are going to learn over here only one transformation that is called the Laplace transform. So if FB are defined for all greater than or equal to t greater than or equal to 0. See, FB just defined function. I didn't say that F is continuous or something like that. F is just defined function over here. Then the integral F bar S equal to F of F bar S. F bar S is a symbolical representation of the transformation. Laplace of F of t. Ft is my function. You are applying transformation L. L stands for Laplace here. And the definition is integration 0 to infinity e to the power negative st ft dt. This kernel here is e to the power negative st, e to the power negative st, where s is a parameter, s is greater than or equal to greater than 0, sorry, strictly greater than 0. And this Laplace of ft is another symbolical representation is capital F of s or f bar of s. That means my function t, function of t is to be converted in terms of the function of s over here, function of s here. So Laplace transform of the given function means answer must be in terms of the parameter s. And if you go back in a reverse way, means if you're taking the inverse Laplace transform, that means your question starts with the parameter s and you are coming back to your function f of t. You are coming back to your function f of t, right? So that's what we mean by the transformation. That's what we mean by the Laplace transform and its inverse Laplace transform. Right now, let me just focus over here on the Laplace transform that f be defined for all t greater than or equal to 0, means the interval is 0 to infinity. Then the integral f bar s or capital F of s or Laplace of ft is 0 to infinity or negative st ft dt. This is possible provided this integral exists. Integral exists means integral converges, right? If integral diverges, you're getting infinity, no, making no sense. Let me go for some of the examples. Suppose Laplace transform of one constant function. So let me replace ft over here, 1, so e to the power negative st in indefinite integral, improper integral. So let me take that fix one b over here and b tends to infinity. So 0 to b e to the power negative st dt. Integration e to the power negative st divided by negative s. 0 to b, negative 1 over s is constant, pull it out. 1 over e to the power negative st can be written down over here as 1 over e to the power xt, st. Range is 0 to b. Replace your t by b and t by 0, second fundamental theorem of calculus. You're going to get 1 over e to the power sb minus 1 over e to the power 0 is simply 1. This is negative 1 by s is outside, don't forget this part. As you apply b tends to infinity, b is infinity, 1 over e to the power infinity is infinity, 1 over infinity is 0. So 0 minus 1 is negative 1, negative will become positive 1. So I'm getting just 1 by s. So Laplace transform of 1 is 1 by s. Please keep in mind this thing. Again, I'm telling you that if your ft is a constant function or if it's a function of t, Laplace operator, Laplace transform transforms your function from t domain to parameter s, t to s. Look at over here, constant to s, like this. And for inverse transform, inverse Laplace transform, that means if you are taking inverse of 1 over s, you're going to add 1. So it's vice versa process. It's vice versa process. T to f of s, and then after f of s to t, like this. This is your Laplace. This is your inverse Laplace. Suppose I take some algebraic function t to the power 1 ft equal to t. So if I replace this ft equal to t linear function, then e to the power st and t. Now how can you get the integration of this one? U into v rule. Integration by parts. Exponential function stands last, so this is my v and this is my u. E to the, again, it's a product rule or u into v rule with improper integral of first kind. So let me first fix my b as b tends to infinity for this one, and u into v, u as it is, integration of v minus derivative of u and integration of v, u into v rule, Liet rule. If you apply this one, in that case, you are going to get, look at here, you're going to get negative 1 over s, t over e to the power st and this one and this one. This integration is simple, but here, you can see here, if you apply that b tends to sorry, t equal to b, and here also t equal to b, replace this t by b and e to the power st t by b. So b over e to the power sb minus 0. Negative 1, let me write these two integrals separately. So negative 1 by s, let me pull it out, and b tends to infinity, and this one. If I write b tends to infinity, this is 0 of course, but b tends to infinity in the numerator over here, that will provide you infinity. E to the power b is infinity, e to the power infinity is infinity, so it is infinity over infinity form, means it is indeterminate form. Standard indeterminate form Calc 2 course, that means you can go for L'Hopital's rule to get the limit. So L'Hopital's rule says that take the derivative individually of numerator and denominator. That is the advantage of taking L'Hopital's rule whenever you have 0 over 0 or infinity over infinity kind of functions. So here it is, because this 0 over 0 and infinity over infinity, they are two standard indeterminate forms. So after getting either 0 over 0 or infinity over infinity, you can only apply L'Hopital's rule. There are another indeterminate forms like 0 times infinity, infinity minus infinity. If you have in this type of forms, convert this form to either 0 over 0 or infinity over infinity. Sometimes you may get some exponential form, indeterminate forms like 1 to the power infinity, 0 to the power infinity, infinity to the power 0, something like that, this exponential form. Whenever you exponential form, at that time, always start with your ln function, take logarithmic function, take the help of logarithmic function, and then after convert that function to either infinity minus infinity or 0 times infinity, and then convert that function to standard form of 0 over 0 or infinity over infinity. You know these indeterminate forms by your Calc 2 course. So I don't want to go into the depth of that one, because all you guys, they know this thing. So I took the derivative of b with respect to b is 1, and here e to the power sb derivative is s times e to the power sb. S times e to the power sb. Now if I pass the limit as b tends to infinity, e to the power infinity, so 1 over infinity is 0, so it is 0 here. And here b tends to infinity, 1 over infinity is 0, so 0 minus 1, that is negative 1 over s out. So here negative 1 over s and negative 1 over s, negative will become positive, and 1 over s square. Means Laplace of t, that is equal to, we started with function t, so Laplace of t is 1 over s square. I don't want to read this one as 1 over s square, but I would like to read this one as 1 factorial over s square, because you know 1 factorial is 1 over s square. I don't want to look at this one as s square. I want to look at this one as s to the power 1 plus 1. 1 here and 1 plus 1. Whenever I have t to the power 1, t to the power 1, that means exactly 1 I have to replace. I have to take here 1 factorial over s to the power that 1 plus 1. That means if I increase my polynomial order, suppose it is quadratic polynomial t square, here it has to be, because as 1 is 1, so 2 should be 2 here. So 2 factorial over e to the power 2 plus 1 is 3, 2 plus 1. So here, and here you have to have same number. Suppose I want e to the power t to the power 5. So here it is 5 factorial, s to the power 5 plus 1 means 6. In general, suppose I have t to the power n, I can write n factorial divided by s to the power n plus 1. So that is the general form for nth order polynomial, or Laplace transform of nth order polynomial. Look at here. Look at here. Blah, 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 like this, whatever I explained to you. Right? Good. Suppose somebody asked me to find the Laplace transform e to the power negative 3t. Good. Ft is now e to the power negative 3t. So e to the power negative 3t. E to the power, just apply the definition. Base is same. You can add the power. So e to the power s plus 1t. Go for the integration. E to the power negative 2t means e to the power negative 2t divided by negative 2. This is constant. So divide by that number. Otherwise, you can go for s plus 3 equal to u. Same thing. Calc 2 course, just simple integration. Pass the limit. If you pass the limit, you're going to get 1 over s plus 3. That means whenever e to the power negative 3t, right now we are just proving different kind of examples like exponential function, trig function, algebraic functions, constant functions, and finding the Laplace transform. Later on, we are going to use this one directly. So whenever e to the power negative 3t is there, this negative 3 is over here 1 over s minus a. So e to the power, suppose negative 3 is your in general a, e to the power at is Laplace transform 1 over s minus a, 1 over s minus a. So e to the power negative 3t, 1 over s plus 3, here a equal to negative 3. So e to the power at is 1 over s minus a. Suppose e to the power negative of at is 1 over s plus. So signs are opposite. Here negative at plus at plus a plus at negative a, s 1 over s minus 3, like this. Laplace transform of some trig function sine of at, use the formula, just plug this sine of at in the formula, integration 0 to infinity e to the power negative st ft dt. Ft is sine of at. So e to the power negative st and ft, I gave you that integration, solve that integral, and then plug the values, plug the range, you will be getting a over s square plus a square. If your hyperbolic function, in hyperbolic function will be replaced over here by minus sign. So a over s square minus a square. If you have cosine of at, that is a over s square, or sorry, s over s square plus a square. You have the parameter s over here too and here too for cosine function. And cosine hyperbolic is same as sine with s in the numerator, s over s square minus a square. So please keep this thing in mind. Just for example, suppose a equal to 6, so Laplace of sine of 60 is replace your a by 6, 6 over s square plus 6 square. So that's just the answer. It's simple. The advantage of Laplace transform is you can find the Laplace transform of discontinuous function too. Yeah, this is a discontinuous function. You can over here, you will see here from 0 to pi, value of the function is sine t, that means trig function, and then after from t greater than or equal to pi onwards, it is simply 0. It is simply 0. Right? So whenever we have this type of discontinuous function at that time, we can start like this. Integration 0 to infinity, ft dt. Ft is this one. But my integration range is divided into two parts, 0 to pi and pi to infinity. Between 0 to pi, it is defined sine t. So my ft is sine t. Ft is sine t. This is the definition. Ft is sine t now. Between pi to infinity, my ft is 0. So ft is 0 means everything is 0, no need to write. Means I'm concentrating only over here, e to the power negative st sine t. If you remember, I gave you one of the formulae previously in chapter 3, example number 10 or something like that, in LCLR circuit. I gave you one definition, one integration e to the power negative, e to the power at cosine bt, e to the power at cosine bt is e to the power at divided by a square plus b square, a at sine bt, a sine bt minus b cosine bt. So that's the integral I'm going to use over here. So e to the power at, a is negative s, divided by a square plus b square. A is negative s square and b is 1, sine bt, b is 1. Negative s means a sine bt, negative s sine bt, b is 1, minus b is 1, cosine of bt, b is 1, cosine t. Plug the values, plug the range, and you're going to get that is equal to, this is the answer, 1 over s square plus 1 and this one. So you can find the Laplace transform of some discontinuous function also. So that is the advantage. Okay, the formula I used over here, that is this formula. I think I already provided you this formula. If you don't have, or if you forgot this formula, write down this formula and then write it down in your very first formula sheet of derivative and integration formula sheet on the bottom part. I will allow you to write it down, this one in the formula list. Okay, but don't write anywhere else. I just want the same formula on the integration derivative formula sheet. So e to the power at cosine bt is e to the power at a square plus b square a sine bt minus b cosine bt. And e to the power at cosine bt is e to the power at a square plus b square a cosine bt minus b sine bt. Right? A cosine bt minus b sine bt. Just make sure, I think here it is plus and here it is minus, if I'm not wrong. Please make sure, please make sure. I gave you that formula in chapter 3. I may be wrong over here. Maybe here it is plus, but please double check. Yeah, otherwise I think that's fine. The sign is there, then it's plus over here. When if plus over there, then in that case, take the plus sign over here. Take the plus sign. Take the plus sign. That's it. That's the only difference. Okay, guys. Then after, this is the example. This example that is from your practice test, 11C. 11A and B I solved. 11A is this one, 11C is this one. 11B I would like to solve later, not right now. Example number 11D. Question number 11, last example. Ft equal to sine of 4t plus 5. Now you know the Laplace transform of sine of t or sine of at, but you don't know the Laplace transform of this type of function 4t plus 5. So first of all, use your trigonometric knowledge. Sine of theta 1 plus theta 2 can be written as sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. Using the formula sheet, second page, very first formula sheet, second page, unit circle, below the unit circle, you're going to get that formula. So sine of theta 1 plus theta 2 is sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. And cosine of theta 1 plus theta 2 equal to cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. So make sure about the signs. Okay. So once you have, I wrote down the formula 2. So my theta 1 is nothing but 40, theta 2 is nothing but 5. Just plug the values over here. Once you get this one, cosine 5 is a constant term, pull it out the Laplace transform. Sine 5 is a constant term, pull it out of Laplace transform. And then go for, or pull it out and then go for Laplace transform. So now Laplace of sine 40, that is simple, 4 divided by s square plus 4 square. Cosine 40 is s divided by s square plus 4 square, right? So that's how you can get the Laplace transform. That's how you can get the Laplace transform of the given function. Just apply the definition, use improper integral of type 2 mostly. If it is required, try to use the indeterminate form, apply definition, use some trick concepts, whatever you have a knowledge of your trick functions, trigonometry, use that one and try to get the Laplace transform. That's easy. 7.1 is damn easy. You are not doing anything new in 7.1 only except applying the formula. But now I'm merging my 7.1 with 7.2 because 7.2 is nothing but the inverse Laplace transform. Inverse Laplace transform. Now guys, be careful, be careful. Laplace transform of 1 equal to 1 over s, as I told you. That means if I take inverse Laplace transform both sides, so inverse of 1 over s, that is equal to, I'm getting my function, because inverse and L inverse will get cancelled out and you're going to get the identity operator. L times L inverse or L inverse times L, that is equal to identity operator, and they commutes. Okay, so Laplace transform of 1 is 1 over s, implies that inverse Laplace of 1 over s equal to 1. Laplace transform of t was 1 over s square, 1 factorial over s square. 1 factorial is a constant term. Whenever constant is there, just send to other side whenever you're writing the inverse Laplace transform. So inverse Laplace transform of 1 over s square is t. That is simply t. You can realize this thing well better over here in third formula. Laplace of t square is 2 factorial over t s cube. Actually 2 factorial over s to the power 2 plus 1. But 2 cube, s cube. Or you can write s to the power 2 plus 1. So inverse Laplace transform of 2 factorial over s cube is t square. 2 factorial over s cube is t square. But 2 factorial is constant. Pull it out and then divide throughout by 2 factorial. So I'm getting 2 factorial over here. So whenever you're looking for the inverse Laplace transform, make sure that you don't have any other function except s. We don't even want any constant over here. We just want the parameter s here. That's it. Just parameter s. Same way, t square is 2 factorial. As I told you, t to the power n is n factorial s to the power n plus 1. So if you take inverse both the sides, so inverse of 1 over s to the power n plus 1 is t to the power n divided by this constant n factorial. Look at here, t to the power n by n factorial. You will be using this inverse Laplace. You will be playing with this combination so many times now onwards up to the end of the syllabus. Laplace of sine of at is a over s square plus a square, but a is a constant, so pull it out. So inverse Laplace transform of 1 over s square plus a square is sine of at divided by a. Sine of at divided by a. But you cannot do the same thing for cosine, because for cosine you have parameter s here in the numerator. So Laplace of S or inverse Laplace transform of S over S squared plus A squared is cosine AT. S, you cannot pull this S out. You have to have S inside the inverse Laplace transform. Same here with the trig function and hyperbolic function too. So cosine of AT is S over S squared plus A squared, and inverse of S over S squared plus A squared is cosine AT, as I told you. Hyperbolic is just the sign difference, that's it. And otherwise it is same as the trig. Cosine hyperbolic AT is sign difference, otherwise same as trig. Exponential function, just now I told you that e to the power AT, here it is minus A. If it is minus A here, it is plus A here. So inverse Laplace transform 1 over S minus A is e to the power AT. I request you please try to go through these formulas, all these formulas twice. I included all these things in your formula set. Laplace of this one equal to this one. In your formula set, all these formulas are included. I can show it to you, just wait. Where is it? Look at here. Look at here, Laplace of 1 is 1 over S, inverse of 1 over S is 1. So everything is included over here. Most of the formulae are there. So in the applications, you are going to see this thing that we are not determining the unknown function ft directly, but rather than we are able to solve for the Laplace transform f of s, and then we solve fs by the inverse Laplace transform. Laplace transform has number of applications. Most of the electrical engineering courses, mainly control theory, part 1, part 2, then statics, civil engineering course. So many courses are there in which when math is involved, and if you're looking for the integration like this, at that time, people don't rely on simple integration techniques, but people rely on the Laplace transform. Most of the authors, based on your engineering disciplines or STEM majors, I would say, people are using Laplace transform instead of using the other methods of solving the integral. Laplace transform is the another tool of solving the differential equations. Please keep in mind this thing. So whatever differential equation, whether it's first order or higher order, what it may be, differential equation with initial conditions can be solved using the Laplace transform. I'm not just talking about the differential equation, I'm talking about the initial value problem. And practical problems are always either initial value problem or the boundary value problem. They are not just simply a differential equation. So they are initial and boundary value problems. And that's why Laplace transform plays a big role solving those real life problems based on the initial value problem and the boundary value problem of differential equation of any order, higher order, first order, what it may be, right? So that is the another advantage of the Laplace transform, another advantage of Laplace transform. Other way around, I would say that mainly engineering major and in general, the STEM major would not survive without Laplace transform. Very frequently, you might have seen at some of the places, or you're going to see this thing so many times in future, the use of Laplace transforms. So please make sure about this thing. And if you're not good with this one, you will be struggling a lot in your majors, mainly when the math is highly involved. So please make sure this thing and try to go through this chapter. Some people, they are facing some problems, solving the problems of examples of Laplace transforms. I will try my best to convince you. If you have some doubt, we can discuss over here in our review session, daily review session of 10-15 minutes. But for that, you need to work daily. If I teach you today, you have to go through the same stuff today so that you will have some doubts tomorrow and we can discuss the same thing in our review session. But if you don't read, you will not be having any doubts and you will be good and I will be good too, right? But if you are working, you will have some doubts and that will help you a lot. And I'm always there to help you out. Always, you know this thing better, right guys? One more thing, guys, student evaluation is now open. So please try to fill up that form, student evaluation form. If you're satisfied by this course or whatever I've been doing over here by providing you everything well in advance, your practice test assignment, formula sheet, class notes, YouTube videos, everything. I tried my best. I have explained to you everything. So if you feel that or if you are satisfied and if you think that I have finished this course with full justice, please try to fill up the student evaluation form and try to give your remark. Yeah, it's the first time experience for all of us, for you too, and as well as me, that for online teaching. So we have some constraint, but trust me guys, I have tried my best. It's not that easy, but I tried my best. Yeah. Usually compared to our in-class teaching, we are putting almost double, or I would say 2.5 to 3 times more than 3 multiplied by 3 times we are utilizing over here. So please guys, I hope you will understand. Okay guys, let me continue. Okay, so this is the inverse Laplace transform, or I would say the relationship between Laplace transform and inverse Laplace transform. I would like to provide you a couple of minutes, and I just want you to focus on all these formulas right now. Just pay attention, try to look at this one and how the Laplace or inverse Laplace transform goes for the given function. So please do this thing. Please do this thing. And if you have any question, please let me know. I can give you 2 minutes. Then after we'll again proceed further. Thank you. Hello. Let me know, please, once you're done. Done? I'm asking you guys, done?
Yes, sir.
Are you guys done?
Yes,
Yeah.
sir.
Okay. So now let's go for the inverse Laplace transform. Now guys, I don't want you to, I just want you to keep your calculator handy. Please guys, keep your calculator handy. If you don't have it, I can give you 2 minutes. Go out, grab your calculator and come back. And come back. Okay. So you have your calculator, right? That's what I understood. And now let me start with this one. Look at here, guys. I want to solve this example. S squared plus 6s plus 9, s squared plus 6x plus 9 divided by s minus 1, 2, and s plus 4. S minus 1, s plus 2, and s plus 4. Okay, guys. Good. Good. Let me share my whiteboard with you and I will let you know how to solve this example. Once you are done with this example, almost you will be done with your Laplace transform. Almost. It's not that difficult. Okay. So it is asked to us to find the Laplace transform of or inverse Laplace transform of, what was the example? S squared plus 6s plus 9 divided by s minus 1, help me, s minus 2 and s plus 4 if I'm not wrong. Right, guys? Yes or no? Hey, guys, I need your response. What you guys are doing? Yes or no?
Yes. Yes.
Good. Look at here, guys. I'm looking for inverse Laplace transform, but first of all, I'm just using my knowledge of Calc 2. So let me write like this: s squared plus 6s plus 9 divided by s minus 1, s minus 2, s plus 4. S plus 4. Because it is a linear power and power is 1, power is 1, power is 1, and all are different s minus 1, s to the power 1, s to the power 1. That means my method of partial fraction says that I can write s minus 1 over here, I can write b over s minus 2 over here, I can write c over s plus 4 over here, right? That is called method of partial fraction. Method of partial fraction. Method of partial fraction. Am I right, guys? This can be written as a times s plus 4 and s minus 2 plus b times s minus 1 and s plus 4 plus c times s minus 1 and s minus 2. And here it is s squared plus 6s plus 9 divided by same thing 1, 2, and 3, and whole divided by here also we have same thing s minus 1, s minus 2, s minus 4. All these common denominator will get cancelled out. So that will get cancelled out. And we are getting s squared plus 6s plus 9, that is equal to. Now I want to arrange this right hand side in the descending order of s. That means I can write, let me first take the product over here, then after I will write in the descending power of s. So I can write s squared plus 4s minus 2s, so it is plus 2s minus 8. Plus b, here it is s squared, then plus 4s minus s, so plus 3s minus 4. Plus c, here it is s squared minus 2s minus s, so minus 3s plus 2. Now if I want to arrange this one in the descending order, so a plus b plus c, and outside it is s squared. Plus I can write 2a plus 3b minus 3c, outside, sorry, it is s to the power 1. 3c, outside it is s to the power 1. Agree, guys? And plus I have negative of 8a, negative of 4b plus 2c, and bracket complete. And left hand side is s squared plus 6x plus 9. If I want to write it down this one in the form of the matrix, or if we compare the coefficients, I'm going to get a plus b plus c equal to 1. Then after I'm going to get 2a plus 3b minus 3c equal to 6. And my final equation is negative of 8a minus 4b plus 2c equal to 9. These three equations are there. These three equations are there, right? That means I can write this one in the form of coefficient is 1, 1, 1, and then dotted line. And then I'm getting, oh my gosh. Wait, guys. Okay. So I'm getting here 1. And then after I have 2 here, 3 here, -3 here, I'm getting 6 here. I have -8, I have -4, I have 2, I'm getting 9 over here. All of you, please use RREF in your calculator. RREF, and give me the numbers, please. RREF in your calculator and give me the numbers. I may ask you any one of you. Don't disappoint me, guys. Yes, Nina?
I'm still looking for it, sir.
Okay. Some other guy? Alex? Alex?
Yes, sir.
What is RREF?
I don't know.
I'm getting it, sir. Hold on. I got -28.2.
No, I want
25.
I want fraction. I don't want decimals. Please, I want fraction.
Oh, fractions? Hold on.
And here you are getting, I hope, 100, something like that. What are you getting here?
Yes, 100,010,001.
Thank you. And now this corresponds to your A, this corresponds to your B, this corresponds to C. What are the values you are getting over here?
-141 over 5.
141 over 5.
-141 over 5.
Are you sure?
That's what the calculator is saying.
Okay. Did I do any
25.
mistake? What, 25?
Yep.
25, then?
21 over 5.
21 over 5. Why I'm getting such a beautiful number? Let me just double check, guys. So here it is, s square plus 4s minus 2s. So plus 2s minus 8. I'm good. Here is s square plus 4s minus s. So plus 3s minus 4. I'm good here. S square minus 2s minus s minus 3s plus 2 over here. Yeah, I'm good.
Sir, hold on. Question.
All of you are getting the same number, guys.
Oh, wait, hold on. No, I messed up.
No.
I thought I misread your handwriting.
I have -16 over 5 for the first one,
Yeah,
Okay.
that's right.
and 25 over 6.
Wait.
I misread your 4 as a -9. Oops.
Okay. Paul, go ahead.
-16 over 5,
-16 over 5 makes sense. Second one is
25 over 6,
25 over 6. Third one is
1 over 30,
1 over 30. This makes sense. Yeah, this makes sense to me. All of you are getting the same numbers, guys. I think Paul is right. Nina? Nina.
Yes, sir, I got it.
Good. Harris? Harris? Not working, right?
I don't know how to do it on my calculator. I still have to look up a video or something.
Okay. You are not getting this one, how to get this number or how to use RREF, please take the help from somebody else in the class, okay? He or she will help you out. Okay, so my A is this one, -16 by 5, B is 25 by 6, C is 1 over 30. Let me go back and plug these values of A, B, and C just to get here, guys. Plug these values of A, B, and C over here. over here. So what am I going to get? That means, may I erase this part, guys? Shall I erase all this part? Or if you want, you can take the picture so that I can erase this one. I can start the new page. Window, no, I don't have that one. That option over here. Alternating, no. Oops, what I did. Okay. What is this? Shall I erase, guys, this one? With the example, I don't have any other space. Please help me. If you want, you can take the picture and I can proceed further.
You can erase it.
Okay, good. How can I erase this one? Oh my gosh, that bar toolbox is gone. Okay, let me close this one and let me share this one again. Okay, it's here. Now, so my A, please keep these numbers in mind, negative 16 by 5, 5 by 6, and 1 by 30. Okay, keep these three numbers in mind. And I'm going to start with this one again. So let me do one thing. Let me just erase this part without formatting. Okay, guys. So now let me write that is equal to, erase this one too. Okay. So let me plug the values over here now. So I'm getting negative 16 by 5. Please try to look at the way of writing s minus 1. Plus, here it was b and s minus 2, right? Okay. Plus b is 25 by 6 and 1 over s minus 2. C equal to 1 over 30 and 1 over s plus 4. Right, guys? And left hand side is nothing but s square plus 6s plus 9 divided by s minus 1, 2, and 4. I am asked to find the inverse Laplace transform of this function. So let me write inverse Laplace transform of the first function, inverse Laplace transform of the second function, inverse Laplace transform of the third function. And you can see over here, I just pulled all my constants out from the inverse transform. So that is equal to negative of 16 by 5. Now look at here, guys. I think I need to, I can erase this part too, right? Let me erase because already I used my numbers now. Okay, sounds good. And let me change my color too, so that you can come to know what I'm doing now. So I am doing something like this. Let me use the black one. Okay, so actually what happens here that you know that e to the power, see, you have to have the complete idea about the Laplace transform and the inverse Laplace transform whenever you are solving this example. So I would say that Laplace of e to the power at equal to 1 over s minus a. You know this thing, right? Here in this example, I want 1 over s minus 1. Means my a equal to 1. So e to the power 1 times t. Agree, guys? I want s minus 1. Look at here. So here it is, this one. So this implies that I can write inverse Laplace transform of 1 over s minus 1 that is equal to e to the power t. Am I right? All of you agree with me, girls? Nina, I can't see you.
Yes, sir.
Yeah.
Arrange your picture, please. I can see only your ceiling. Okay, good. Now, so here it is. I can write that is equal to e to the power t. E to the power t plus 25 divided by 6. Same here. s minus 2. So instead of a, now a equal to 1, I can write a equal to 2. So that is equal to e to the power 2t plus 1 over 30. And I want e to the power a equal to now negative 4, right? If I take this a equal to suppose negative 4, so negative negative will be positive here. And here it is e to the power negative of 4t. So that is the inverse Laplace transform of this function. That's how you can find the inverse Laplace transform. Does it make sense? And you can see over here, I told you that when you start with the inverse Laplace transform, you are starting with the parameter s, and you are ending up, as an answer, you are ending up with all t's. Look at over here, all t's are there. This one, and this one, all t's. Right? If you are writing, suppose Laplace transform of some function, suppose e to the power 5t, that means it is equal to just 1 over s minus 5, like this. So Laplace of, here you have to have function t, and here you are getting parameter s, where s is greater than 0. Right? So please make sure about this thing whenever you write the Laplace transform. If you have any doubt, you can ask me. If you don't have any doubt, we can go for the next one. Shall we go for the next one, guys? Shall we go for the next one?
Sure.
Okay. Good. So let me stop sharing this one and let me go through. Can you see this page? I don't think so. Let me share my screen with the class notes now. Okay, so look at over here. That's what I did over here. Exactly same. Same example. I think, yeah, same example. Replace me, see. I just gave you the hint over here for question number 12, B and C part. Suppose I ask you this example, inverse Laplace transform of 1 over s cube plus 5s. Naturally, you can take your s out, so you have one linear factor, so 1, because power of s is 1, so I can write a over s. And here's a quadratic function, that means I can write bs plus c over s squared plus 5 for the quadratic term. Right? You know that this all comes from the method of partial fraction. So if you take, start with this one, take like this, and then after take the LCM, as squared plus 5s, and try to arrange this one in the descending order. So a plus bs squared plus cs plus 5a, left hand side is 0. Left hand side is this one. So a plus b, if you compare the coefficients, you're going to get a plus b s squared. Nothing is mentioned over here, just 1. 1 can always be written as 0 times s square means 0, because s square is there. So let me write 0 times s square. Because s is there, s plus 5, there is, oh yeah, cs is there, right? So cs plus 5a. Because s to the power 1 is a cs is there, let me write 0 times s to the power 1. And then after constant term is 5 of a, 5a is 1, s to the power 0, s to the power 0. Now I can compare the coefficients, a plus b equal to 0, c equal to directly 0, 5a equal to 1, so a equal to 1 by 5. I have a and c. Naturally, I can plug the values, I can get b. I don't have to go for my RREF. This is very simple calculation. Once you found your a, b, and c, just go back and plug it over here. And once you plug it over here, that means you are writing your denominator, product of denominator in a simple plus or minus linear function, and then go for inverse Laplace transform. Once you go for inverse Laplace transform, you're going to get 1 over a is 1 by 5, so 1 by 5 is out, inverse of 1 over s. Whenever you write Laplace transform, please listen to me carefully. At that time, make sure about your 5 and s. I would like to write my 5 like this. Look at here my writing, 5 like this and S like this. Don't get confused between 5 and S, and don't make others confused between 5 and S. You have to make separate your 5 and S. It should not look like same. Otherwise, you will be losing your points. So 1 over 5 and inverse of 1 over S. Inverse of 1 over X, that is equal to 1. Negative 1/5, I just took it out. And inverse of S over S square plus 1. That is, what is inverse of S over S square plus 1? This is nothing but cosine function, right? Cosine of AT equal to S over S square plus A square. So here my A is, or A square is 5. So A is root 5. So 1 over 5th cosine of root 5D. That is the answer. My next example is inverse Laplace transform of 2S plus 5 over S minus 3 squared. Same thing, guys, exactly same things. We are not doing anything new. So first of all, let me write, this is now a repeated roots, repeated factors, linear power. So 1 A over S minus 3 and B over S minus 3 square. B over S minus 3, B over S minus 3 square. So 2S plus 5 equal to AS minus 3 plus B. Descending order. Compare the coefficients. You are getting A equal to 2 and B equal to 11. Go back and plug it over here. Take inverse Laplace transform. That's what example demands. So inverse Laplace transform. Take this 2 out. Take this 11 out. 1 over S minus 3. That is simple e to the power 3t. What is 1 over S minus 3 square? 1 over S minus 3 square. Now guys, look at over here. I am looking for, just look at over here. This is simple. This is simple. You can use the formula. 1 over S minus 3 to the power 3t, just like your previous example. But now I have a square. I have a square. Again, let me share my screen with you. I'm looking for 11 over S minus 3 square. I'm looking for 11 over S minus 3 square. Let me erase this part. So, inverse Laplace transform of 11 of S minus 3 and square. 11 out and inverse Laplace transform of 1 over S minus 3 and square. Now, which function gives me S minus 3 square? Guys, please make sure here. Which function gives me S? Forget about minus 3. Where is S square is there? You know this thing that Laplace transform of t that is equal to 1 factorial or 1 over S square. Agree? 1 over S square. We are going to learn first shifting theorem. So first shifting theorem. First shifting theorem says that if you have any function, any ft, any function of t that is multiplied by e to the power t, that is equal to integration, Laplace of e to the power at is s minus a. Agree? Am I right, guys? Laplace of e to the power at, that is equal to s minus a. Whenever you have product like this, whenever you have some product like this, so Laplace of e to the power at ft, that is equal to, guys, please pay attention over here. Here, let me consider something like this, t equal to, yeah. So let me start like this, t equal to this one. If I write this is equal to, if I multiply by e to the power at, so I'm going to get 1 over s minus a, because s is replaced by s minus a for this one, s minus a, right? And this t is there, t square. So actually, if I multiply like this, that means what I'm doing, I'm not changing my function s square, but s is replaced by s minus a. S is replaced by s minus a. By multiplying this exponential function, s is replaced by s minus a. And this itself is known as the first shifting theorem. This itself is known as first shifting theorem. I gave you this one as the formula also in the formula sheet, but I would appreciate if you can go through the first shifting theorem, right? First shifting theorem. So 1 over s minus 3 square, 1 over s minus 3 square. Now 1 over s minus 3 and square, I'm looking for the inverse of this one. So that is equal to, your a is replaced by 3. So that is equal to 2e times e to the power 3t. That's it. And then just go back and plug it over here. So 3 times e to the power 3t. Okay, that's what I did over here. Let me clear this one. And let me stop sharing and let me go for my function again. You can see over here, t times e to the power 3t. So it is something like this that we are using over here, the first shifting theorem. I will be taking care of this example again once we are done with first shifting theorem. If you want, I can give you again 2 minutes, try to look at these two examples. Before we proceed further, please try to look at these two examples. And if you hand out, please ask me. Okay, guys. Shall we start this new article? If you just want to focus on Laplace transform, I don't mind. We can start this new article tomorrow. Or if you want me to start the new article, I don't mind. This is the Laplace transform of derivative. I don't want you to confuse right now. I just want you guys to work on Laplace and its inverse Laplace transforms. Is it okay? Or if you want, I can continue. It's up to you. It's the inverse Laplace transform and its derivatives. What do you prefer, guys? Most likely we are going to finish your syllabus by tomorrow. Yeah, by tomorrow. Monday review session, Tuesday exam. Wednesday review session, Friday final. So we are in time, don't worry. Yes, what do you prefer, guys?
Sir, since this is the last thing that we have on the syllabus,
You have any doubt?
Here.
Have a good day.
You too, thank you. Yeah, any doubt, guys? Girls, if you have some doubt, you can ask me as a part of the review session. If you don't have any doubt, we are good.
Sir, can we talk now since you said your email about the questions? You sent me an email.
Yes, yes. I ask you to ask me the same questions by email, whatever you wrote it down in the email. So let me,
I understand.
we can discuss that thing. Just